We have reached an extraordinary point in the history of science. For some physicists believe they are now on the verge of having a single theory that will unite all of their science under one mathematical umbrella. In particular, this theory would unify the great bastions of modern physics, the general theory of relativity and quantum mechanics. Since general relativity describes the large scale or cosmological structure of the universe and quantum theory describes the microscopic or subatomic structure, but both quantum mechanics and relativity fail when applied to each other's subject matter. The theory of everything is the unification of these theories would explain both the very big and the very small. But what is the theory of everything, and what is the magnitude of Stephen Hawking's contribution to science? In particular, the theory of everything would unify our understanding of all the fundamental forces in our universe. There are four such forces that physicists know of: gravity, which keeps planets revolving around the sun and is responsible for the formation of stars and galaxies; the electromagnetic force, which is responsible for light, heat, electricity and magnetism, and which is also responsible for holding atoms together; the weak nuclear force, which acts inside atomic nuclei and is responsible for certain kind of radioactive decay; and the strong nuclear force, which holds together the protons and neutrons in atomic nuclei and is therefore crucial to the stability of matter. Combining these all four fundamental forces, or in other words quantum mechanics and classical physics, into a unified approach which explains the laws of the universe has been one of the greatest challenges for scientists. While no one has actually been able to come up with such a theory, nonetheless, Stephen Hawking was able to elucidate a formulation that unified quantum mechanics and classical physics as it pertains to the description of black holes. According to physicists, theory of everything, also called final theory, ultimate theory, theory of the world or master theory, is a hypothetical, singular, all-encompassing coherent theoretical framework of physics that fully explains and links together all physical aspects of the universe. A string theory and M theory have been proposed as theories of everything. We will discuss about these theories in detail in our another videos. Over the past few centuries, two theoretical frameworks have been developed that together most closely resemble a theory of everything. These two theories upon which all modern physics rests are general relativity and quantum mechanics. You may think, so what is the big deal? Well, the big deal is that while both classical and quantum mechanics that describe the world around us, one general relativity, a theoretical framework that only focuses on gravity for understanding the universe in regions of both large scale and high mass, like stars, galaxies, cluster of galaxies, etc. On the other hand, quantum mechanics is a theoretical framework that only focuses on three non-gravitational forces for understanding the universe in regions of both a small scale and low mass, like subatomic particles, atoms, molecules, etc. Each of two pillars of modern physics describe its respective area of inquiry, the very smallest and the most massive things in the cosmos, with astounding accuracy. But both quantum mechanics and relativity fail when applied to each other's subject matter. Quantum mechanics successfully implemented the standard model that describes three non-gravitational forces: a strong nuclear, weak nuclear and electromagnetic force, as well as all observed elementary particles. Another model that also included gravity would be known as quantum gravity theory. Some researchers believe that a string theory is such a framework and fits the bill for a theory of everything. A string theory posits that particles are actually one-dimensional string-like entities vibrating in an 11-dimensional reality. The vibrations determine the different particle properties such as their mass and charge. Einstein also began to search for a unifying theory in the 1920s according to the American Physical Society. He had never fully accepted the strange paradox of quantum mechanics, and he believed that the mathematics describing electromagnetism and gravity, the only two forces known at that time, could be combined into a single framework. Now let's go to know the contribution of Stephen Hawking to understanding the black hole. Hawking's arguably greatest contribution was the discovery of the Hawking radiation, which is one of the biggest breakthroughs in the 20th century. It detailed an unprecedented understanding of black holes as well as the interplay between quantum effects and general relativity. The concept of the Hawking's discovery is ingenious in that it is simple yet profoundly creative. Hawking discovered that a black hole is like a bitumen tablet that fizzles out in water it can dissipate in time. This turned the scientific community on its head because the common description of classical physics stated that black holes are super densely packed objects of matter and that nothing can escape from them. To understand the science behind the discovery, we should start by understanding some basic concepts of physics and how they interplay. Black hole. A black hole is defined as a densely packed region of space. You can imagine it like a stress ball made up of matter where the gravitational pull is so strong that nothing can escape out of it. Around the stress ball, there is a circular region of space which encapsulates it, and the perimeter of this circle is known as the event horizon, which can be thought of as a ball that separates what the reality we can perceive from which inside the black hole. We cannot see anything beyond this point. The second law of thermodynamics states that the amount of entropy of a system will always increase, which means that entropy is a measure of disorder and the universe is always naturally moving toward a more disordered state. But anything that has entropy must also have temperature, meaning that it should radiate energy. However, the whole point of the black hole is that it holds everything so tightly that nothing gets out. So how could this be explained? What Stephen Hawking cleverly proposed is that black holes actually do radiate energy, but this process can be described through a quantum understanding of the world rather than classical one. Quantum mechanics state that what seems like an empty space is actually not empty. It is alive with the dynamic activity of simultaneous creation and destruction of the energy on the subatomic scale. Particles and antiparticles are created in pairs where one particle has positive energy and the other has negative energy. One particle is matter and the other is thought of as antimatter. Then they rapidly collapse back together in a process known as annihilation, so that no energy is created or destroyed in accordance with the first law of thermodynamics. Because this process happens so fast, it is suggested that these particles are virtual because they have not been detected. What Stephen Hawking suggested was that if the particles are created very close to the event horizon, then they do not need to be annihilated together because one of the particles can be sucked into the black hole. And in order for the laws of conservation of energy to hold, the particle that goes back into the black hole needs to have negative energy. Thus, if the black hole receives negative energy, this is in effect its losing energy and thus losing mass. Energy and mass are interchangeable through Einstein's equation E equals to mc square. So, that would indicate that black hole is emitting energy and is getting smaller as a result. This is the brilliant idea that showed that black holes are not actually all black and dark and they do not last forever. In the words of Stephen Hawking, if you feel you are in a black hole, don't give up. There is a way out.